as Sergi just mentioned, I'm going to be talking about a use case, or 3 years of use cases really in the automotive industry of using WebAssembly. Predominantly, we're going to focus on using WebAssembly for improving privacy by applying privacy-enhancing technologies with WebAssembly. Now, even though we're focusing on automotive and privacy-enhancing technologies, a lot of what I'll be talking about applies to general service development, general edge, and embedded development as well. So a lot of these points can be used in pretty much any project. It's just how deep you want to go into this stack. But I'm going to go pretty deep in this, but without going too technical in terms of code examples or anything else. My initial goal was to do a demo of this platform, but it took over 2 hours to demo it. So to do this in 25 minutes, I'm going to talk through it, but at the end of this deck, there will be a QR code. If you use the QR code, you can reach me, and I can set up a demo for you. It'll just be a video. It won't be me involved, but I can send you the video, and then you can watch the demo yourself and see how everything works in the real world. So, first of all, I work at the moment partly for a non-profit foundation called Omnifi Foundation. We've been existing since 2019, and we work collaboratively with different organizations, predominantly focused on safety, so how to build safety into systems. This includes privacy, but it includes other safety mechanisms like fairness and equality and bias modeling as well. We've been self-funded for our entire time. We haven't received funding elsewhere. We predominantly do ecosystem work with other large companies, and we fund ourselves through that model. 94% of the services we've built with WebAssembly are pretty much use standardized frameworks such as Spin and Wasm Cloud. We haven't built everything from the ground up like we have with this use case. So this is a fairly unique use case. So our landscape last year was to work on 3 projects where they overlap for the companies we were working with. One is called Taira, which is what I'll mostly be going through today. Taira is a privacy tool to make sure that your data is secure going in transit and at rest. Another one is called Ray. Ray is our responsible AI toolkit. So it's a toolkit that we're using to make sure that people can build AI models safely, not invading privacy, and ensuring that they're also sustainable in their training modeling as well. And then finally, Narmio. Narmio is essentially the core component of both of these projects. It's a data space, essentially. Simply put, it stores your data, stores it in a graph, and allows it to be retrieved. But we're doing something pretty interesting with Narmio for the automotive industry. So the problem with automotive, I'm not trying to stay with automotive, but we do get a lot of work because they do have a problem. They're spending a lot of money with data collection and data storage at the moment. Our experience is between 10 and 100 million, depending on the automotive company we've worked with, is just on collection and retention of data. So it's a lot. Data is not cleaned between the owners, so when you go from one car to another, the data is kept. Nobody ever cleans that data from that vehicle. So there is a potential issue in terms of fingerprinting and figuring out what people are doing with their car. And data is typically sold. So all automotive companies that I've met sell your data. That's part of their model because their margin on actually selling vehicles is quite slim. So, and that data being sold doesn't benefit you in any way. And data is portable. Now, this is an interesting problem that most OEMs don't realize or haven't realized until we've raised it. We have GDPR and data regulations across the world, over 100 different data regulations. And when you travel with a vehicle and it's sending data to the cloud, when it drives from across a border, for example, if it drives from France to Germany, where is the regulation meant to be? Where is it applied? And actually, it's meant to be applied where the data is being sourced. So in that instance where you're crossing a border, the data regulation being applied actually should shift. And that is a problem at the moment. That's not actually correctly implemented in any OEM that we've worked with. So our solution, what we've built for multiple OEMs, I think that we're into double digits now with the automotive companies we worked with, is always make sure the data doesn't travel. So we keep the data in the vehicle, most of all. We use zero-knowledge proofs and model weights to transfer information back and forth. So there's not actual data, but we will transfer a zero-knowledge proof down the chain, meaning a computational proof, or we will send model weights for AI systems down the chain as well. But we won't actually send any data to any services. And we use WebAssembly as a tool for retrieval augmentation. That means that when we have a model running in the vehicle, when we use AI in a vehicle, we will then use WebAssembly to do additional augmentation on how to use that data or how to use that model. So it's a pluggable system, essentially, for the vehicle. And then personalization, fine-tuning, and training happen on the device. So we don't do anything on the cloud with any of the projects we build. We do everything within the vehicle itself. Meaning our vehicles or the vehicles we've built with OEMs are private. So as I said, we've worked with quite a lot of different OEMs over the years. This is just a handful of what we can mention, but there's more than double that we cannot mention at this point, including some Chinese OEMs as well as some Americans as well. So I've been working with automotive companies for a long time, since 2012. I've been working with safe data spaces since 2015, including working with the W3C on building new standards for data spaces, secure data spaces, and with the EU as well in data space regulation. And we built our first proprietary wallet in 2022, just in time for the first Wasm I/O, which I presented in 2023. Very briefly. So you can find that video on YouTube if you want to see some of the other use cases we had at the time. And then we're now on our third proprietary automotive wallet that we did in 2024. We're now looking at homologating what we've built already and turning it into an open source project, so OEMs don't need to come to us anymore and build yet another proprietary system. They can actually just take something off the shelf and plug it in. And we're fully open source. We're not building products for people here. So Taira is the first project I mentioned. It's secure and portable tooling. So we want to bake privacy in there. We want to make it really simple and reduce the technical complexity of applying privacy into your solutions and your services, automotive being the most complicated. So the main product we have sits in a consumer-facing angle. It can sit in the dashboard of a car, it can sit on your phone, and it's called Taira Wallet. It's a secure agentic wallet, meaning when I say agentic, it interacts with things around you by understanding context and behavior. So you don't need to tell it what to do most of the time. It just learns from your behavior. We have Shield, which is a VPN, essentially. It's a little bit more complicated than that, but we're not going to talk about that at all in this presentation. And then we have Vault, which is built on Narmio, and it's a private data space that's enterprise scalable. Again, these are all going to be open source components, but at the moment, we're rebuilding Narmio out through an homologation process in the open source community. So I'm going to go through a really quick use case, and this is what I wanted to demo, but this use case will take a long, long time. So I'm going to absolutely zip through this use case, and feel free to grab me after this and ask for more details about this use case, but also how we actually achieve certain things if you have any confusion. So imagine at the moment, you're a family, you own a car, all of your knowledge of your family, of your behavior, your kids going to school, you going to work, your grocery shopping, is being learned on your devices and in the vehicle, and it's stored in the vehicle itself. So the vehicle understands your daily habits. The vehicle looks through your calendar, your email, or whatever else it can get access to through Bluetooth on your device or through the vehicle itself, and finds family tickets for a flight. So it knows you're taking a flight today. It starts to warm itself up in preparation. It checks the road conditions to know how long it's going to take to get to the airport. And then it reminds the driver with a notification, hey, you need to set off at this point if you're going to make it in time for your flight. This is a real-world use case we've built, and it's a use case we've demoed multiple times. So in this use case, your family enter the vehicle, the journey is mapped preemptively. This is part of the agentic capability. It's already in the vehicle, gone into the mapping system and said, this is the route they're going to need to get to the airport on time. So you sit in your vehicle, it's nice and warm, your seat's in position, the mirrors are in position, the route's already there, it knows you're fully charged, you're ready to go. As the journey begins, the vehicle asks whether you have parking reserved at the airport. You can use voice interactions. We don't want drivers tapping screens or messing around with anything, so you can use voice interaction to speak to the vehicle and say, actually, I do need parking, can you reserve it? It reserves a parking space for you. Again, with the agentic interaction. It knows how to pay for it because it's got a wallet capability built in, and it learns what you need from your parking. Then it does a little bit of rerouting as well because a parking space may not be close to the departure lounge. The family arrive on time. Whilst waiting for the flight, the vehicle then figures out at rest using the agentic wallet on your watch and in the phone that you're at rest, you're waiting, you're not going anywhere, your flight's in another 30 minutes. So then it says, OK, I'll notify them and say, hey, do you want your car cleaned? We know you haven't got it booked in at the moment. You haven't cleaned it for 2 months. Maybe you want it cleaned while you're away. So you confirm that, it books that in as well. So you now have cleaning booked in while you're away on your trip. The next stage is you arrive at your destination, you have a rental car. You go collect the rental vehicle, and as soon as you collect the Bluetooth, it syncs all of your settings. It knows where your seat needs to be, where your mirrors are, exactly how you want your car set up, essentially. And it does that instantly as soon as you get to your vehicle. Then it sets up insurance for the trip. It sets up your toll passes because it knows you're driving on some, let's say, German roads that need toll passes, and it knows your route based on where you're staying with your Airbnb booking, and it books those in as well, and any parking you require, and then looks at the rest of your itinerary. Maybe you've got a visit to a castle booked in or some museums booked in. So it figures out all those routes for you preemptively on this new vehicle. And again, this is not going anywhere. This is all within the vehicle itself. And then the family are notified during their trip their car is now being cleaned. The way this works is we have a standardization for digital keys in vehicles. It creates a digital key dynamically. It gives it to the cleaning service. They get access to your vehicle, clean it, and once they're done, the vehicle relocks, deletes the key, and you are notified that your vehicle has now been cleaned. It's ready for you when you get back. And then there's some of the use cases we demo typically, and it will be included in the video. One is essentially food and drink planning as well. So it knows kind of the places you go to when you drive and can say, OK, you've got 2 kids in the back that really like having baby chinos at Starbucks, and your wife really likes getting a Frappuccino. We know you need to charge in 90 minutes. We will book you into a service stop, reserve your drinks, and then make sure that you get your car fully charged within that time while you're getting your drinks. We can do that basically through an open ecosystem model. We have a relationship with Starbucks in this case, and we can make sure that system allows you to have a very fluid experience during your trip. Again, all within the vehicle. Nothing leaves your vehicle or your devices. So the important thing, how do we actually build this kind of system? Or how have we built this system in the last 3 years? It's evolved a little bit, but this is our latest version. So all vehicles that I've worked on have hypervisors. Typical cloud technology is very familiar. We have a hypervisor within the vehicle itself. It has a real-time operating system, typically Linux in all the examples we've worked on, but it can be other operating systems. It's not really important to what we're doing. And then we have an in-vehicle infotainment system. Often it's Android Automotive, not Android Auto. They are 2 different things. Sometimes it's a Android open source project operating system instead. And then they have, often these days, if we're talking about electric vehicles, which are the only vehicles we've worked on in the last few years, they have 2 AI-enabled stacks. They either have Nvidia Drive or Mobileye IQ from Intel. So we're looking at 2 different architectures. Essentially, we're trying to do machine learning in the car. The important thing here is we're not just doing inference. We are training in the car, so we need to have quite a lot of power. The cars we've worked on have all got 2 GPUs. The reason we're looking at 2 GPUs these days is self-driving. We can't get self-driving. We haven't got that capability, but we're building cars with that in mind in the future because you have to build a car with a 10-year roadmap. It has to have hardware that will last 10 years. So we're looking at 2 different systems here. One's guaranteed to be Intel, one could be ARM, or in one particular case, it could be a Chinese OEM's proprietary chipset, which we've had to work with as well. Why are we using WebAssembly in this case? We want our system to be pluggable. Most of the time, if you're using Nvidia Drive, you'll be using containers. It's a container-based Linux operating system. It's pretty much what you're used to using on the cloud. But it's not great if you're trying to build an OEM that's efficient, that uses electric power efficiently and does machine learning in there, then sending containers up and down the wire doesn't make sense. So we want a sandboxed environment that's efficient. We're sending a couple of megabytes down the wire, maybe, rather than sending an entire container down there. So we want to build a zero trust security model, and we can do that with WebAssembly out of the box in the same way we would do it with the cloud. It's polyglot tooling. This is great because if we go to most OEMs, they already have a tool set. They're used to working with one technology or the other. With WebAssembly, we don't need to convince them to change to a different programming stack. We can just say, use the programming stack you're familiar with and compile it down to WebAssembly. And we use WIT to build the worlds around that, and then they can use like BindGen, for example, to generate the interfaces to that if they need to. And then it's efficient. With an EV, you care about the energy usage you're using within the vehicle. So we don't want to drain the battery when we're doing machine learning within that vehicle. WebAssembly allows us to do that because it's super efficient. It's not running an entire container. It's not got Kubernetes in there. It's just a small runtime that's used when it's needed. And it's near native performance. So we get a fluid experience. If you're talking about the in-vehicle infotainment system and all the applications there, you want to tap that screen and immediately get something back that's smart. You don't want to have a delay there. So with WebAssembly, we get a fluid system all the way down the stack, all the way back up to the infotainment system. And we use WIT and WAC more recently to create our worlds around that model as well, so we can create custom worlds based on the information we want to get from the vehicle. So why don't we use Spin, and why don't we use Wasm Cloud, and why don't we use any other framework at the moment? We use them on our services. We build them with these frameworks. We don't build everything custom. But the reason we don't use it is because they're not built for that. They're built really well for building cloud services. They're not built for embedded systems and machine learning training. So we did reach out to Fermion. We've reached out a few times, and this is pretty much the evergreen response I will always get every time I tell them I'm working on a specific project, that we're always a little bit ahead of where they are at the moment. And again, we're very specialist in what we're trying to do. But we do use them everywhere else. It's a great stack. So what does our data space look like? What's our training model look like inside the vehicle? How do we actually do this machine learning training when everyone else is struggling to do inference with WebAssembly? How are we getting to do the training in a privacy-friendly way? So we start off with a security model really deep down into the vehicle. We use Intel to build a secure enclave if they have Intel. If they're not Intel, then we use the Open Portable Trust Execution environment. So what we're doing now is we're building a custom framework in Rust, really low level, starting with how to secure the data and the processes and the computation within that vehicle. We don't need to do this. We could make it a little less secure if we wanted to, if the OEM didn't have the capabilities, but this is what we're doing in vehicles. And then we built a core technology on top of that, and we built a graph model on top of that as well. It's a generic graph model. We're using essentially JSON-linked data for our graph model. On top of that, we also have AT protocol support now. We have solid support, which is RDF, and we have some other graph technologies. They're all pluggable by WebAssembly. We've built the primitive worlds for graph models, and then we build the extensions for different protocols with WebAssembly. We use gRPC and protocol buffers to do some extensions to native components, so things we're not going to compile down to WebAssembly. And we do that securely with TLS as well. And then we have a runtime, and we have a WebAssembly host. Now, most of the time, we're using Wasm time. Wasm time works in vehicles really, really well. It's a familiar stack. We don't need to do anything special. We're not really a constrained environment for resources like you might be with more IoT devices, like a vehicle's quite powerful. In some cases, we will use the micro runtime instead, where we are a little bit more constrained. Or, again, if we're using Intel and we want the Intel SGX security model, we use micro runtime because it has that built in. Where with Wasm time, we would need to build the OPTE capability for the secure enclave ourselves to make sure the data is secure. And then we build our worlds, like we typically can do now with Preview 2 of WebAssembly and the component model. We build our custom worlds in that vehicle of what's represented. For example, if somebody pushes a brake pedal, we have an event there. We have a data model of how compressed it is. That's part of the world we can build in that vehicle and use that for machine learning within that vehicle. And then we use something very familiar to some people, which is WASI-NN. We have our system interface for neural networks. I worked in 2019 with WebNN. It's very, very similar. We can do inference with that model to a limited extent. We're not talking about limited inference, though. We're talking about training here. So how do we do the training? We wrap at a low level libtorch and Candle, two different runtimes we wrap at a low level with the secure runtime to do the training within the vehicle. So that's how we get the training, essentially, and then we build a WIT around that. That doesn't solve the fact that most of the time when you're doing machine learning in a vehicle, the reason we're collecting data and aggregating data is we want to build really big models. We want to build models like LLMs, for example. And we want to do that by massively scaling the information we bring in, huge ingests, which is where you get the 100 million from, pull that data in, and then do massive MLOps on that and start training those LLM models based on all that data you've aggregated. And then you send those massive models back down to the vehicle. But you have loads of data in that case. You have a massive trove of data lakes and data meshes where you're collecting data. This doesn't solve the privacy model. We want to train in the vehicle, but if we're still collecting the data to train the central models before pushing them back down, we haven't solved any issues here. So we built Ray. And Ray is our responsible AI toolkit, hence the name Ray. We're not very inventive with our naming. So Ray has guardrails. It's built on familiar responsible AI toolkits, so it has Nvidia guardrails built in. It has some other guardrail tooling built in. And it's built essentially on PyTorch and supports TensorFlow and JAX as well. So it's a familiar set of tools. With Ray, we start with a safety by design intelligent tool set. We start off by thinking about how we build AI models that are fair, remove biases, and also provide us with checks in an MLOps process to make sure that when we deploy them, we're not propagating new biases or creating a system that is essentially unsafe. We're not building self-driving cars here, we're building a consumer-facing system, but we still want to make sure it's safe for people. So Ray is a safety by design intelligent toolset. It supports existing MLOps processes. We're not building an MLOps platform with this. What we're trying to do is just say, if you have an MLOps tooling, we will allow you to deploy your data where you need to, run the training exercise, do the validation exercise, do the model deployment exercise, all in the same flow. And then we orchestrate the training workloads. Now, this is where we start getting the privacy benefits with Ray. So we can gather all of our fleet of vehicles. In our demo use case, we had 18,400 vehicles, I think. We want to orchestrate all of those fleets and make sure that we understand which vehicles get which models. Not all the vehicles are the same. Some will have different access to different data. Some will be on different demographics. For example, if we want to deploy a model that's specifically to the Japanese market because the demographic there has certain needs, we will deploy a model into that market separately than we will deploy into Europe or the US. And it will depend on the model as well. So we want a way of orchestrating that, and we do that across a global edge network of 100 different POPs, again, using WebAssembly here. And then we want the guardrails out of the box. So we use existing tooling. We're not building product here. We're building capabilities for OEMs. And again, as I mentioned, it supports JAX, PyTorch, and TensorFlow so far. It's PyTorch-based, so we're using Torch script to get that portability. And then we run it through WebAssembly. So how does that look? How's our service architecture? We've seen the PDS, but what does the service look like? Really simple high-level overview. I can go into detail of these parts later if anybody has questions. We have a studio toolkit to begin with. It's a web application. You go in, you add the models, you upload some ONX models, which are portable. You add some WebAssembly components built against a WIT, and then you choose which fleets you want to deploy to. It's a very simple dashboard application. Then we have a composer. Now, the composer it's a single node here, but it's a massively complicated system, our composer. And it runs on Kubernetes. It's partially powered by Spin for our service APIs and using key value store. And then it's partially built with other technologies as well, including traditional Docker containers. And then we have our training mechanism. When I'm talking about MLOps, it fits in here. So we have a training mechanism where the composer will then say, we need to retrain these models, we're out of date, or we want to aggregate these models and provide a new model for the vehicle. So we have our training mechanism there, and then we have baselines. Now, baselines are, if we go back to the idea of LLMs and transformers and machine learning, baselines are our base models before we've customized for any demographics and done any of our training. And then once those baselines are retrained, we will tell the composer we have new models that need to be shipped out. And then we use our edge network. And now our edge network in this case is Fastly. We build absolutely everything on Fastly for this orchestration of these workloads. The reason for that is they are global. We don't have to build any infrastructure. We can build WebAssembly, so we can build with a familiar toolkit. Even though it's just preview 1 so far, we can still reuse our Rust compilation, which we're using in this case, and then deploy to the edge network. And then Fastly can allow us to make sure that when we push models back up the chain, we don't push them into the wrong region, because we can detect the POP that's received that model and ship it to the correct region, making sure we're fully regulatory compliant. So the edge network, in this case, it picks up from our library of models, ships them all down to the fleets, the correct fleets, to receive the models. The models are also shipped with WebAssembly components that are meant to do the retrieval augmentation and do any logic within those vehicles as well. And those vehicles then start training and start enhancing their capabilities based on what they're learning in the vehicle. It could be some people driving a Porsche Taycan are really aggressive with a brake pedal, and it's learning about that behavior. It's learning that is unique to that model, but it's certain behavior that it can then figure out better routing or better energy preservation or other things. Once it's learned over a certain period and we hit a certain level of capability within those models, they ship back up. They go back up through the agent network, back up through Fastly, and then we store them in our object store. And then they go back to the composer. The composer then redoes the averaging baselining and then ships them back down to the vehicles again. So we have this complete cyclical process of training within the vehicles. At no point does data leave any of these vehicles. It's always the models and always the weights. We never ship anything where we're taking data from these vehicles at any point. This means that when you leave your vehicle, because it's in a secure enclave, the data can stay there, but it's not accessible to anyone else. The keys are between your devices and the vehicle, not between anything else. Even the OEM can't get access to that data in that vehicle. And then finally, we have Ray Vision. We actually have a toolkit that will explain exactly how the model works, how the vehicle's being trained, and we call it X-Ray Vision, which is the entire reason we call it Ray Vision, just so we could use the name X-Ray Vision here. That's a dashboard, and it will provide all the explainability for the entire models within your fleet, so you can understand what's happening within your fleets and how you're using your models effectively. So, conclusions. For the projects we've been doing, it's a 3-year project. We use Fastly to deploy most of our stuff to begin with. That's our base starting point because we can deploy WebAssembly programs into Fastly effortlessly, and it deploys into all the POPs, and we get a very efficient way of building our services to begin with. I recommend giving it a go if you want to experiment with WebAssembly. Then we use Spin and Wasm Cloud as well, various degrees depending on what we're doing. We've been using Spin for a long, long time. And we build that for our service architecture. We try and use WebAssembly where we can, because then we get the benefit of reusing WITs if we can reuse WITs and components, and also because we're mostly using Rust in everything we do, we can just compile down to the different targets quite easily and reuse components. So we have code reuse, which is what I've just mentioned, between the edge and the cloud. We're using a lot of similar components without having to think about the target we're building towards. And then we have privacy-first inference, which is great. That helps you get so far, but training is where the powerful thing is. If you're still collecting data to train, then privacy-first inference is a little bit weak. It doesn't really solve the privacy issues. And in our case, we found it's rarely needed to collect any data. We've taken one company to collecting data to collecting 0 data, because they actually do all of their analytics in the vehicle using federated analytics. So we don't think there's a need to collect data most of the time. And WebAssembly is efficient, safe, and now we found it incredibly easy. So again, you don't need to go as deep as we have in building a stack here. You can just build your services with Spin, for example, or Fastly, and it's incredibly easy to build straight away. In minutes, you can build a web service. Where we've gone has taken us a little bit longer because we're building our own framework for vehicles in this case. But there's that depth of where you need to be, where you can find that position, that sweet point for your project. So all of our work at the moment, again, it's going to get homologated into open source work. We're going to put it into LGPL for the applications, and then we're going to license all of the subcomponents with MPL as well. Not just for OEMs. Our private data stores operate in all of the spaces. If you want to reach out and see the demo and maybe find out some other information, feel free to find me on Blue Sky, and feel free to interrogate me about anything, any part of this, and I will share as much as I can, because, again, we're a non-profit foundation. We're not here to sell a product or anything proprietary here. Okay, thank you.
The Wasm module that you're actually using on the car, do you have OTAs updates for those? How do you manage the whole supply chain, software supply chain for those things?
Yeah, so OTA is done with a typical OTA model within the vehicle. So that we have a couple of different stages. We can use something like Pelion, which is the ARM spin-off. We can use AWS, where they have their own way of distributing updates to the vehicle. That's fine. We're not updating the infotainment stack or anything else. We're only updating the Wasm and the machine learning models. Those OTA updates are done primarily through Fastly at the moment, so we ship them directly down that way. And we have a couple of services in the background on scheduling and like cron jobs and things like that on Kubernetes. But our OTA updates are purely the models and the WebAssembly components. We don't update anything else. The OEM uses its existing updating infrastructure to update the rest of the stack. Anybody else?
You mentioned that you're only working on electric vehicles so far. Is there anything inherent to what you guys are doing that like requires that, or are you planning to, support other kinds of propulsion systems as well?
We try not to do cars at all, if I'm honest. It's an accident that we keep doing cars. But we've been doing electric vehicles because they have the GPUs in them. Electric vehicle companies keep coming to us, and that's the problem they want to solve, is how to use these GPUs to do smarter things within their vehicles, because they're trying to build a service model on top of the vehicles. So that's the only reason we're doing that. You can't do that with ICE vehicles in this case.
Okay. Are you targeting like other kinds of vehicles, other segments, aviation, anything? I'm just curious.
We would love to target aviation. We've worked with a German aviation company and tried to do that, but their model is a lot slower. Even cars are 10-year models. These guys are even slower than that. Oh, and they have very protected environments of how to do deployment in that space. We have done projects with them, just not this type of project.
Okay. I might come find you later. That's super interesting.
No problem. Anyone else? Feel free to find me afterwards. Happy to answer any further questions. And I'll be here tomorrow as well. Okay. Thank you.